When there are two stereogenic centers in a molecule, there are four possible stereoisomers. Take a look at this example. I'm going to put four different things on these two carbons. And now let's assign the absolute configuration. Notice the term absolute configuration, R or S, according to the Kahn-Ingold-Prelog convention for assigning stereochemistry. Let's take a look first at this carbon. I'm going to assign the absolute configuration of that carbon. I need to assign the priorities of the atoms attached to it. And we do that according to atomic weight. Here's bromine is 1. Here's chlorine is 2. Carbon is the next one. And the fourth priority, the lightest one, is hydrogen. Now I need to orient this molecule so that the lowest priority group is away from us, and it is already. So we're ready to assign the absolute configuration by starting at 1 and going in a circle to 2, and then furthermore continuing around to 3. And we know that we're going in a clockwise direction. So we're going to call that R. And if I do the same thing for that stereogenic center, I will assign iodine as 1, fluorine as 2. It's heavier than carbon, which is 3. And hydrogen back here, this is 4, the lowest priority. And what do I have? I've got the lowest priority group away from me, so I can go in a circle, and I will be going from 1 to 2, around to 3. There's 3 there. I find myself going in a counterclockwise direction, and this is the S stereochemistry. Now let me write another stereoisomer. 2 carbons attached, put the bromine and the iodine in the same places. But I'm going to switch the chlorine and the hydrogen. And I'm going to switch fluorine and the hydrogen. And now when I assign the absolute configuration of that center, because those two ligands have been switched, it's the S configuration. And when I assign this one, because I switched 2 of the groups, this is the R. So I have 2 stereoisomers. Let's look at another possibility. The carbon here and the carbon here. I'm going to put the bromine just where I have in the past. I'm going to leave the iodine where it's been. I'm going to put the hydrogen and the fluorine like they were up above. The hydrogen and this chlorine. I'm going to switch these 2 guys. The fluorine is going to be here and the hydrogen here. And the fourth possibility would be the mirror image of this, where I have the bromine and the iodine fixed, like they have been, but the chlorine is back, the hydrogen is toward us. And now here the hydrogen is back, and the fluorine is toward us. And to assign these absolute configurations, R or S, we'll use the same conventions, do the same kind of thing, and we'll see that this one is the same as up there, R. And this one is reversed, like it is up above. That's S. Nothing different so far. When I get to this guy, I'll see that this is not the stereochemistry I have up above. It's the opposite, like over here. So I'm going to call that R, of course. And this one will be S. So we could summarize these 4 stereoisomers that we have and say that we have an R, S, and an SR. Carbon 1 and carbon 2. Here we have an RR and an SS. Look at this. We have 2 pairs of enantiomers. That's fine. But what if we take a look at any other 2? Let's say that we have a bag that has all 4 of these in it, and we reach in and pull out 2, and they're not this pair or that pair, but they're these guys. These are not the same thing. There are stereoisomers. They're not mirror images of each other. There's something different. Or if we pull out these 2, we would say the same thing. These pairs that I've indicated here in this lighter blue here, this brighter blue, are called diastereomers. So now we see we have two different types of stereoisomers when we compare two that aren't the same. Somehow they're spatially different. We either have enantiomers, they are non-superimposable mirror images, or we have diastereomers. Everything else, this is an odd definition. You don't very often see a definition based on a negative. But basically, in stereochemistry, that's exactly what we have. We have two types of pairs of stereoisomers. We can compare two stereoisomers and see that they're mirror images that aren't the same. We call those enantiomers. Or we compare two stereoisomers and say, they're not mirror images, but they're not the same. They must be diastereomers. Take a look at one more example. I've drawn a 6-carbon chain here, and I'm attaching hydroxyl groups to these carbons. But to be different on the end, I'm going to make it a double bonded to oxygen. We'll put hydrogen there so everybody knows. That's a hydrogen. So we have OHs along the chain. And I'm going to ask you to tell me how many stereoisomers there are. To answer that question, we need to pull out a formula that is universally used to say how many possible stereoisomers are of a certain molecule. The definition is the number is equal to 2 raised to the power of the number of stereogenic centers. So all we have to do is figure out how many stereogenic centers there are. To do this carefully, I want to draw in the hydrogens here so we don't get confused. And there are 2 hydrogens attached to this carbon, so this is not a stereogenic center. It doesn't have 4 different things. And there are only 3 things attached to this carbon, so this is not a stereogenic center. Each of these carbons has 4 different things attached. So each is a stereogenic center, and the number of stereoisomers is 2 to the 4 equals 16 possible stereoisomers. And as it turns out, these will come in pairs of mirror images that are not superimposable. So there are actually 8 pairs of enantiomers. Any other 2 that we compared we would call diastereomers, but there are special pairs that are mirror images, and they're enantiomers. And there are 8 of those pairs if there are 16 stereoisomers. Now I picked this molecule for a reason. One of these pairs is glucose. And you know glucose, most likely, it's a sugar that plays a central role in metabolism. So it's very special. The pair of enantiomers is called glucose. We need to be able to say which enantiomer we're talking about when we're talking about the glucose isomers. And so there's a special way of actually designating that called D and L. So of the 2 glucose isomers, one of the enantiomers is D, and D-glucose is the one that plays the central role in metabolism. So this is very important. It's very important in sugar chemistry. The 6-carbon compound I've written up here is a typical sugar, has a hydroxyl group on every carbon except one, and that one has a carbonyl. So stereochemistry is extremely important in the sugar chemistry field, and we'll talk more about that another time. To summarize, there will be as many stereoisomers total as there are in the formula 2 to the n, where n is the number of stereogenic centers that the molecule has. There will be pairs of enantiomers, and any 2 stereoisomers that are not enantiomers will be diastereomers.